Thanks for attending the seminar today. For those of you that may have seen a version of this talk, it is very much the same. So not offended if you don't want to watch it all over again. But this is going to be just a quick overview of the whole science case of looking at resolved X-ray jets with a high resolution X-ray telescope. We've, of course, been doing this with Chandra now for over 20 years. And I hope we get to do this with Axis as well. And I love this quote from Dan Harris a few years ago, that after all these years, decades of study, we still don't really know what jets are actually made of or how they work. So, okay, how do I change slides? Sorry, I'm using a PDF. There we go. Right, so jets from AGN are really not well understood systems. We still have a lot of questions about even just their particle content, their speeds, especially how the kinematics of these jets, we know they start off highly relativistic. How does that evolve? That of course depends on things like the particle content, their duty cycles, and of course the big picture, which is how does this all sort of map to impacts on the galaxy and on the intergalactic medium, and of course all the questions about jets themselves, such as what makes them look the way they do. There's a huge range in jet power and morphology. So yeah, in terms of the bigger picture, AGN jets are good cosmological probes. They, blazars, of course, are like lighthouses. We can see them down to very, very early times in the universe, so that those high redshift blazars trace black hole growth at early times. At more moderate redshifts, we can use things like giant radial lobes to measure the extragalactic background light. And of course, all these questions we have about how jets influence the evolution of a galaxy. So just to sort of remind you guys how big of a deal was Chandra for these kinds of studies is basically we weren't tracking what the jets were doing, their morphology and how they look on arc-second scales before Chandra was launched. There was a very few observations. This is 3C273, famous X-ray jet as seen by Rosat. That's what it looks like when you look with Chandra. So you can actually really start seeing what this jet looks like and matching, radio resolution. So Chandra brought about a revolution in the study of jets from AGN, being able to resolve them, and in fact found way more X-ray emitting jets on the kiloparsec scale than we were expecting. So this was a major thing, and there was actually a Chandra News article dedicated to that. At this point in time, Chandra has now detected over 200 extragalactic jets, where we're talking about, features that are mapped to the radio structures. So the relativistic plasma, and also in some cases, the lobes where we detect X-rays. One of our graduate students that recently graduated has made an atlas that's very up to date and shows images and data for all these X-ray jets, if you're interested. So why is this interesting? So most people, when they think about blazars or jets and the X-rays, if they're not actually a source of noise for your science case, you're actually interested in them. With most X-ray telescopes, what you're really detecting is all this emission coming from close to the black hole. So in this radio image at top left, I've put a box around the sort of bright part. That's where your X-rays are coming from. In fact, if you point any telescope at this that's not high resolution, that's what you're detecting. It's dominated by the base of the jet. So a typical sort of jet core or jet blazar will give you this spectrum that's shown at right, the classic blazar spectrum of a synchrotron emission at lower energies, and then inverse Compton, we think, at higher energies. So why would we be very interested in looking at the emission on kiloparsec scales? In the radio, of course, the radio knots, yeah, they're nice, they're interesting. You see these interesting blob morphologies, like in this case, but they're 100 to 1,000 times fainter, and the spectra are pretty soft. So the assumption was that the power dissipated on these scales was really negligible. That basically all the main fireworks are happening, down close to the black hole. but that's not actually really the case, and I'll talk about that in a second. So, but the main thing is also we were just observationally limited. So although radio surveys have been picking up these resolved radio jets for decades, since the VLA, we don't have a lot of really high resolution facilities, and especially like in the optical, you really need something like HST because of the high background. You need really low background and good sensitivity. And in the X-rays, Chandra is really the only telescopes we can use. So before people started doing these coordinated campaigns with high resolution telescopes, we didn't really know what we would see from these jets on kiloparsec scales. And it turns out we see a lot of different things. So sometimes you see something like M87. So M87 shown top left, one of the knots, I'm showing the spectrum from radio to X-rays, and you can see that, okay, you've got something that looks like a synchrotron spectrum, radio opticals, X-rays, diving down. Or in other cases, you have something like Parkes 0637, bottom left. This was actually the first target observed by Chandra, and they were not expecting to see anything other than a point source core. And what they detected instead was a point source core with a nice bright little X-ray jet sticking out. And that spectrum of that jet, or actually those 4 bright knots kind of in the middle, is shown at the bottom right. And you can see there's a synchrotron radio optical spectrum, and then this just booming X-ray spectrum. The X-rays are very hard. So this was a big surprise. And I mentioned that Chandra detected way more X-ray jets than was expected. And that's because we thought most jets would look more like M87, and we were not expecting this second spectral component to show up at all. In fact, it was really hard to explain. The first couple of papers on 0637 basically just kind of threw up their hands and said, we've ruled out everything that seems reasonable, so we're confused. We don't know what these X-rays are. Over the next couple of years, 2 alternative models are mainly discussed. So there's 2 possibilities. The X-rays are produced by upscattered CMB photons from a highly relativistic jet. So this requires you to keep the same high relativistic speeds. So we're talking a gamma of 10 or 15 that you have on the sort of sub-parsec scale. If you do that and you sort of orient the jet close to your line of sight, then you can possibly produce inverse Compton upscattered CMB X-rays. Alternatively, you could just have a second population of electrons that's producing synchrotron emission. It's a second population. Obviously, it's separate from whatever's producing the radio optical. The main problem with that is just we don't know why nature does that. It wasn't, especially back then, predicted by anyone that would happen. But these are wildly different physical scenarios. ICCMB, the electrons giving you the X-rays are really low energy. So you're extending your electron energy distribution down to very low gamma. So this actually means that you need a whole lot of them. And that means that your power requirements go really high. Sometimes they're super Eddington for these models. And then you also need other extreme things like, okay, do you really believe the jet is still going with a bulk Lorentz factor of 15 at 100 kiloparsecs? That's pretty far out. And it is possible that this is happening, but there are reasons to think that in other cases, what we are seeing is a second synchrotron spectrum. So in this case, it's the opposite. So instead of very low energy electrons, we're talking about very high energy electrons, so multi-TeV. So that's a different problem because now you need to accelerate, in situ multi-TeV electrons, 100 kiloparsecs from the core. So how do we do that? But it's a much more efficient process relatively, so the energy required is a lot more reasonable. And you don't need these extreme Doppler factors. You can have mildly relativistic flows, that's fine. So obviously we would really like to know which of these models is correct in general or for subsets of populations so that we can really understand particle acceleration, their particle content, and their energy carried. So if you really want to understand the jet impact on their environments, we need to make some progress here. So here's the problem, and I'm trying, part of my screen is blocked by the zoom controls. Is there a way to get rid of that? Let's see. Oh, there we go. Yeah, so the truth is that although Chandra has been fantastic and has really enabled us to even understand that there is a mystery here in the first place, even with Chandra, we are photon-starved. So this is Parkes 1229.021. This is 120 kilosecond observation. and you can clearly see that there's X-rays coincident with the radio, but there's just not enough photons in this jet to get a spectrum, right? Which would be pretty useful. You would like to know whether these X-rays are hard, whether they're soft. And this is especially a problem as we start to go to high redshift. High redshift jets tend to be more compact. And then you start worrying about things like, are we sure that this is really a jet, a relativistic plasma coming out, or is this maybe just shock heated gas, or maybe we're just detecting a small radio lobe. So obviously having the spectral information is key, but in almost all cases, we have nowhere near enough photons to do these kinds of analyses. Right, so this just repeats what I said. Chandra's detected 200 extragalactic jets, but the vast majority of them have poor spectral information. And low counts hurts you in other ways. So this is, at left is the Chandra image of Park 0920-397. You can see the corresponding ATCA radio image at the right. And you can see this absolutely beautiful little sort of cannonball structure in the jet. It's very hard with even Chandra resolution to, map the X-rays precisely to those different emitting regions. And even if you could do something like deconvolution, which we do quite a bit with Chandra, again, the fewer photons you have, the more of a problem that becomes. So, and then if you want to do something like try to understand the evolution of the jet spectrally, look at something like the X-ray to radio ratio even, it's very hard with such low counts. You just have a really hard time. A significant fraction of jets that Chandra has looked at do not show up at all. So about 40% in the 3C snapshot surveys just weren't detected. Even when we make detections, a lot of times we're talking about one knot or one hotspot, or a few counts from here and there. We've got significant portions of the jet that just aren't detected. So clearly sensitivity is an issue unless you somehow commandeer Chandra and just stare at all the jets for a megasecond, right? So, so this is where we're very limited. Chandra started this by detecting these sources, but I think AXIS is going to be allowing us to get a lot of jets with really good statistics for really doing detailed study and detailed, starting doing detailed modeling, physical modeling. I wanted to talk a little bit about X-ray variability, because this is something that was, again, can only be done by Chandra, obviously, and which I think AXIS will really be able to do very well. So X-ray variability, like detecting the jets themselves, was also not expected. The ICCMB model for the X-ray emission was kind of the most popular explanation over the last couple of decades. So when several of the knots in picture A were seen to vary over just a few years time frame, Herman Marshall published that paper back in 2010, that was really, really surprising. People did not expect that for a couple of reasons. First, ICCMB is, that model predicts X-ray emission, which is completely steady, completely. The cooling time for these low energy electrons is so long. It's ridiculously long compared to the year time frame that we're talking about. And of course, the CMB is steady. Even for a synchrotron model, fast variability of this kind is a little uncomfortable because you can do very simple math to get the emitting volume. And it's really, really small. We're talking, light year scale compared to the size of these knots, which are in the radio, at least, like kiloparsec scale. So this is like 1,000 times faster variability than you would expect, even for the synchrotron models. So, so picture A is kind of our best case. And in fact, Hardcastle et al. Found some interesting, very short timescale variability in one of the hotspots, or in the hotspot of picture A. So just to throw out some work that's more recent, my group's been doing a population study, which is currently under review, where because of our limited photon statistics, we're having to basically do a population analysis. But we analyzed the regions from all the X-ray jets we could that were observed more than once. It was about 50, and looked for variability, which was beyond what you would expect under just normal Poisson small number statistics. And we found an excess of counts that were a little bit variable from what you would expect. Individually, most of these are not at the 5 sigma level, but if you look at the whole population, there's too many of these unlikely variability events. So this was pretty exciting. So I hope this paper comes out this year. But interestingly, we found that that signal of variability in the population increases when you cut out the high redshift sources. And there's a reason that makes sense, which is probably the low redshift jets, the X-rays that we're seeing really are from synchrotron emission, which is the only model that's compatible with variability. But at high redshifts, the CMB goes up as 1 + c⁴. So there's long been an expectation that we should really start to see X-ray bright jets. We should start to see even an impact on the total X-ray luminosity from jets, even with low resolution X-ray observations, just because of the CMB enhancement. And there's some really nice studies out of Neil Brandt's group that have looked at this. And in fact, they find that although the X-ray enhancement at high redshift is not nearly high enough to say all the X-rays are coming from the ICCMB model, they do see an increase, which is consistent with maybe a few percent contribution. So what we're starting to possibly evolve towards is that the X-rays are synchrotron in many cases, most cases. We're not totally sure what's happening at high redshift. And of course, but we would like to have better statistics and to start looking at sources individually. It's there's a limit to how much you can really pull out of these population studies, especially things like timescales are really hard just because we have limited observations. Most of these jets have been observed only twice, which doesn't give you a lot of constraints on the timescale of variability. And yeah, I think I'll skip that slide. So another quick thing I wanted to just mention for AXIS in terms of jets is, of course, there's a number of very nice studies done with Chandra already, especially at lower resolution, where we see X-rays associated with radio jets, but it's not the synchrotron, it's not the non-thermal emission. We're talking about shock-heated gas driven by the jet. So this is like direct evidence of kinetic feedback. This is an example of 3C305, low redshift source. And you can also do nice things like compare this morphology with like O3 emission. So you can directly probe the gas dynamics. This was a paper by Hardcastle et al. 2012. They've done a couple others. Now that's very interesting at low redshift. At high redshift, our existing observatories are going to have a hard time. This is maybe the best case I could find, Parks 1138-262. This is a high redshift source. I didn't write down the redshift. I think it was about 2, if I remember. So in this case, we're looking at Chandra contours over a radio image. So there's way too few counts from the extended emission here to do any spectral fitting. But there's a number of sort of indirect lines of evidence suggesting that these X-rays are shock-heated gas. Okay. So it's pretty key to understand this. We've got just a handful of well-studied examples so far with Chandra. But I think it's something that AXIS will be able to do as bread and butter. And of course, it'll be important when we're trying to disentangle studies of jet feedback from jet physics, because you want to know where your X-rays are coming from, and that's going to require you to have enough photons to actually do the spectral fitting. So that's going to be important. So right, so jet-driven winds might be more common at redshift 2. This is a paper by Nesvadba et al. So I think this is something that, focusing again on the high redshift universe, AXIS is going to give us the ability to make great strides. Even if we just go back to X-ray jets is, interesting in themselves and not just on their impact, but most of the known X-ray jets are at redshifts less than 1, okay? So most of these high redshift jets shown in this histogram are actually kind of marginal detections, or they've been detected with a handful of counts. So we're really we haven't observed really the interesting population yet. And this is just another study recently by Brad Sneos, again, kind of showing, you can see that these jets are just barely detected right now. So these are very faint structures. One thing we can do with AXIS, besides just, enjoying much better sensitivity, is that we will be able to use some of the recent enhancements in deconvolution. So This is an example of a study from McKeough et al. 2016. They used a code called Lyra. I think that's low counts image reconstruction and analysis, because if our redshift limit with Chandra is really about 1, okay, with AXIS at some point we're going to keep probing higher redshift, and then we're going to hit the point where even AXIS is photon limited at redshift, I don't know, 4, and so these kinds of studies that are able to use statistics to kind of reconstruct the density of the X-rays with an image that looks like what you have at left are going to be pretty powerful. The other thing is that AXIS is going to connect very well with multi-wavelength facilities, high resolution imaging facilities, because that's how we're actually going to be able to understand what's happening in these jets. So on this slide, you can see this is 3C273, the first jet that I showed in the presentation. This is pretty much the only one, or maybe one of 2 or 3, where we have this kind of beautiful, exquisite data. You've got these SEDs are starting from knot A at one end and going out to knot H2 at the other end. And you can see this drastic change in the spectral output from X-ray dominated at the one end to radio dominated at the other. And also some interesting little bumps and wiggles in between, which we don't really understand. So we really need this quality of data to understand and start putting physical models in contact with the data. Okay, I think I'll skip over the next couple of slides because I'm pretty much out of time. But yeah, so studies of resolved jets are definitely pushing on the limits of AXIS. In particular, resolution is really critical. Ideally you would be down to the diffraction limit if you could, just because you can see detailed structures in the radio, on less than 0.1 arc second scale. So even 1 arc seconds is presents some challenges due to the scale mismatch. Now, I think with some clever deconvolution type things, we can do better than that in terms of information, but that's, that is important. And also, especially as we go to high redshift, most of the high redshift radio galaxies are small in angular size. They're 50 to 100 kiloparsecs, less than 15 arc seconds. The other, parameters of AXIS aren't as important. Like field of view, of course, doesn't much matter for studying these small objects, but the sensitivity is going to really result in major discoveries. So I will leave it there.
Great. So if you have questions, if you want to raise your hand. So while people are doing that, I'll just ask a quick question about, jets are so important for feedback in terms of shutting off star formation in the really sort of massive galaxies. So how does that kind of connect to figuring out, observing these with Chandra and figuring out the overall sort of energy picture, Eileen?
Yeah, that's a good question. So mostly what I could say is if you've got really good radio and X-ray observations at the same time, usually radio is the most important complement here. Then if you have, again, enough photons to really start doing the spectral modeling, and you can look at things like the rotation measure in the radio, right? Then you can start understanding what you're even seeing. So if you go back to that study of Hardcastle et al, this is these are monstrous papers to read just because there's so many lines of evidence to look at to really understand. But this to prove this is shock heated gas is more than just taking a picture and sort of saying, yeah, it sort of traces around the X-ray lobes, right? You need to really be able to measure the total power. And I think this is I think they showed in this paper that it's it's dominated by this kinetic mode feedback here. Yes.
Okay. Great. Let's see. I don't see other